All right, let's dive in. Think about the code you write today. It's pretty much just text on a screen. But have you ever stopped to wonder how we got here? We're about to jump into the very birth of programming, a time when code wasn't text at all. We're talking physical wires, wooden cards, and literally weeks of manual labor. It's an incredible journey from physical objects to the abstract languages that power our entire world.
So here's the path we're going to take. It all starts way back in 1801 with mechanical looms, long before electricity was even a thing. Then we'll fast forward to the 1940s, this kind of chaotic era of plugboards and wiring, right before a truly revolutionary idea. The stored program changed absolutely everything. And finally, we'll see how punch cards and toggle switches bridged that last gap to modern computing. It's this huge evolution from physical instruction to abstract code.
Okay, so here's our game plan. First, we'll look at the very first mechanical programs. Then, let's call it the headache of rewiring early computers. After that, the massive breakthrough of the stored program. Then we'll tackle the challenge of actually getting those instructions into the machine. And finally, we'll see why we so desperately needed programming languages in the first place. Let's get started. Right, so our story doesn't begin with silicon chips. Not even close. It starts with thread and wood. This is a world where programs weren't code as we know it. They were actual physical objects designed to control a machine. Take a look at this, the Jacquard loom from 1801. It used these punched cards where every single hole, or the lack of a hole, was a direct physical instruction. It was a simple binary choice. Lift this thread or don't lift this thread. You string a sequence of these cards together and bam, you have a complete program that lets the machine weave these incredibly complex patterns all by itself. Now, this is a really critical distinction to understand. For the loom, the holes were the program. They were the actions, the verbs. But fast forward to the 1890 census, and those same holes started to represent data. Nouns like married or single that a machine would then process. It's the same tech, but a huge conceptual leap. It's the difference between a program and the data it works on. Okay, now we're entering the electromechanical era. The idea of what programming could be was getting bigger, but the actual act of doing it was about to become a complete and utter tangled mess. So I want you to imagine an old-school telephone switchboard, but instead of connecting calls, you're connecting logic itself. That was a plugboard. To program a machine like ENIAC, operators had to physically route every signal and value by plugging in this complex web of patch cables. If you wanted to change the program, say from calculating artillery trajectories to doing census data, you had to unplug and rewire the entire board by hand. And this, right here, was the massive problem. Rewiring a complex program on a machine like ENIAC could take weeks. For weeks, this multi-million-dollar computer was just a giant, expensive paperweight. The downtime was completely unsustainable. Something had to give. And the solution that came next, well, it was one of the most elegant and powerful ideas in the history of technology. It's a concept that literally defines every single computer, phone, and tablet we use today. This was the big question that drove everything. If physically changing the computer's wiring takes weeks, how can we get the computer to change itself in just a matter of seconds? The answer to this would define the modern digital age. And here it is, the stored program concept, often called the von Neumann architecture. The truly revolutionary idea was to treat the program, the set of instructions, as just another form of data. Think about that. If the program is just data, then it can be stored in the computer's electronic memory, right alongside the numbers and text it's supposed to process. So this is the whole magic trick right here. The instructions and the data live together in the same memory, and the CPU can grab either one. All of a sudden, there's no more physical rewiring. A computer could be running a complex physics simulation one moment, and then by just loading a new program from memory, it could be calculating company payroll the next. The hardware stays exactly the same, only the software inside it changes. So this new flexibility was absolutely incredible, right? But it created a whole new, very practical problem. If the program now lives in this fleeting electronic memory, how in the world do we get it in there to begin with? Well, for a long, long time, the answer was still punch cards. But this created that classic terrifying problem. What happens if you trip and drop your program? A deck of maybe 1,000 cards all over the floor. The solution was just pure low-tech genius. Programmers would take a marker and draw a big diagonal stripe across the top edge of the entire deck. If they dropped it, the broken stripe immediately showed them exactly which cards were out of order. So simple, so smart. And this led to a really early form of automation. A computer could run its calculations and then punch its results onto a new deck of cards. You could then physically walk that output deck over to another machine and use it as the input for the next program in the sequence. It was a physical workflow, a direct ancestor to the software pipelines and workflows that we use every day. Now, for smaller machines like the famous Altair 8800 that kickstarted the personal computer revolution, the method was even more direct and unbelievably tedious. You'd physically flip a row of toggle switches to set a memory address in binary. Then you'd flip another row of switches for the instructions binary code. Then you'd press the deposit button. And then you'd do it all over again for every single line of your program. And that soul-crushing tedium, that brings us right to the final and maybe the most important step in our whole story. The urgent, desperate need to move away from dealing directly with the hardware. So just try to imagine it. You're either managing these huge, fragile card decks, or you're flipping hundreds of tiny switches. You have to know the machine's internal architecture by heart, every register, every memory address, and one tiny mistake, a single dropped card or one switch flipped the wrong way, could destroy hours, maybe days of work. How could anyone possibly build complex software this way? The short answer is, they couldn't. It just wasn't scalable. The solution then was to create layers of abstraction, to hide the messy details. We moved from directly fiddling with the machine using wires and switches to assembly language, which used simple text codes like add or load. And from there, we finally developed high-level languages, which let us express complex logic in a way that's much, much closer to how we humans actually think. You see, this entire journey from physical cards to abstract logic has been about one thing: hiding complexity to empower people. So I'll leave you with this thought. The next time you sit down to write some code, just take a second to think about all the invisible problems your language is solving for you. Things like memory management, hardware specifics, error checking. These are all problems that the pioneers we just talked about could only have dreamed of fixing.